Last time we finished module 3 and we started module 4, right? So today we just continue our module 4. In module 3, we gotta focus on the 3 fundamental metrics, right? Tie them together by the Little's law, and then we apply the Little's law in many situations, right? Like through the examples. So today, let's go back to the example that we left off last time. We did not have a chance to actually work on it. So let me show you the example. Okay, so we have the airport security example on slide 11. So just imagine if you have to go through LAX today, right? You have to check in with the airline, and then you walk out of the airline check-in, and you are heading towards the terminal. But before you and the terminal, there's a obstacle, right? And that hurdle is the airport security process. So you have to stay in line. Somebody will verify your passport, I mean the ID and the boarding pass, right? And then you need to go through the metal detector, and then finally you would need the luggage. You have to go through some X-ray machine, right? So that's the process that we talk about. Just 1 second, please. Okay, so the question asks us to draw the process flow diagram of this process, right? So beside the 3 stages or the 3 steps that I just talked about earlier, there's a long line of passengers before the first step, but sometimes lines also build up as steps 2 and 3. Step 2 and 3 are parallel. That is, customer go through the metal detector while the luggage is in the X-ray machine, right? So that's all of the information that we have here. And so let me work on this. So I'll go to draw the process flow diagram, right? Okay, so we are in module 4 about process analysis. And we are in the big topic of how to draw the process flow diagram. Right, so technically we try to visualize our process so that we can analyze it better. The first example here is security process example, or airport security. This is, again, this is module 4, and you can find that on slide 11, okay? So after we checked in with the airlines, we already checked all the bags in. We already had the luggage. So we try to go through the terminal, right? So the first, the start point of this process is when we arrive at the line. Right? Just imagine how long it would be at LAX. It's very long, right? So that's why we draw a big triangle to say that we have a very long line over here. So remember, last time we talked about the conventions on how to draw the process flow diagram. So the conventions are very simple. The oval is for the entry point and the exit point, right? The arrows are for the flows. that shows how the flow units go through the process. The triangle is for waiting, for transiting, for queues, for wait time, right? All right, so we stay in the line, and at some point somebody will check our boarding pass and the ID, right? So that's the first resource that we have to go through. So ID and boarding pass. Without these two, we will not be able to enter the terminal. So it doesn't make sense to put the check here at the end of the line. Right? It has to be kind of early on, so that it helps people to be prepared to the final step, right? All right. So and this is called resource number one. So after that, we, with our luggage, we'll proceed with the long lines, and at the end we see the metal detector, right? So you and your luggage will split up. They, in the question, they say that sometimes small lines also build up before the metal detector and the X-ray machine. So it might be a small weight or a small line right here, right? For example, for the metal detector, somebody might have to go through it again. So everybody else had to wait. It is not like straightforward, right? So sometimes there's a small line before the metal detector. But eventually you go through it. So this is a metal detector right here. And that's our resource number two. And then we have the resource number three. So our luggage will have to go through the X-ray machine, right? So we have another resource right here. That's an X-ray machine. That's three. And sometimes there's a line between before the X-ray machine. Just imagine, it takes a lot of time for the luggage to go through it, right? People look at it and rewind the conveyor belt and fit it again. So sometimes it takes a lot of time for the luggage to go through, and then somebody has to visually check the luggage pieces, right? All right, so at the end, you and your luggage meet, and then you exit the process, right? Exiting here means that you are heading towards your airplane gates. So the end of the process is heading toward to the gates. So again, we are using the oval to denote that's a boundary of the process, right? So for the boundaries, we are using the ovals. For the resources, we are using the rectangles. For flows, we use arrows. For weight, we are using the triangles, right? So they are just simple conventions on how to draw the process flow diagram. I hope now you know how to draw it, and then you know how to read it, right? Whenever you read the ovals like this, you know that's the boundary of the process, right? And look at the arrows, you know that this is an entry point, that's an exit point. And along the way, if you see the resources, that's what they are talking about, the steps or the activities that they include in the process, right? The flows will help us to see how the units are going through, and then the triangles tell us that there are some weight over time. There are some wait time over there, okay? So that's the first example of how to draw the process flow diagram. So let's do one more, and hopefully we're gonna quite sure about how to draw the process flow diagram. Okay, so the next example is actually our homework 1, question 22. So let me show you the question first, and then we're gonna draw the process flow diagram of that question. Let me share the question with you. So you know what? At this point, I have a friendly reminder for everybody that we have the homework 1 due next Monday. Okay, it is due already, more than a month, but we are already there, right? So this is the homework 1 part 2. Let me share that with you. Okay, so both part 1 and part 2 are due next week, right? Part 1 is make or heal connect items. So the reading assignments, the 20 online questions are due on Connect next Monday. For part 2, you know what? We have 5 problem-solving questions, but only 2 questions are ready. So next Monday, only question 21 and question 22 are due. Okay, question 21 here and question 22 here. Right, already we would cover them, so that's why only question 21 and 22 are due next Monday. Question 23, 24, 25 will be due later when we are done with the contents. All right, so let me go through this 21 a little bit. So in class, right, we worked on the example about Walmart regarding the inventory turns and inventory costs. But for question 21, you need to work on the Home Depot and Lowe's, right? So you would go here to find your the data, right? And then you would go through this table right here, do all of the calculation. Rest assured that is very similar to what we worked on with the Walmart example, right? So question 21 should be within your reach, easy reach, I would say. For question 22, it is another application of the Little's Law, okay? So we talk about an online university with like 23,000 students, right? Roughly speaking, that's a size a little bit smaller than the size of our campus, right? So in this online university, there are 4 stages: general education, and then foundation, major courses, and then concentration courses, right? So the student will have to go through all 4 stages. Stage number 1, 6 months, and then stage number 2, 9 months, on and on. And down here, I also give you some numbers down here, okay? So at first, if you just read this question, it's very confusing. It's really hard to imagine what I ask you and what you need to do. So to help you with that, I would like to draw the process flow diagram of this online university. And hopefully that will help you to answer all of the questions here. All right, so let me draw the process flow diagram of this question with you. Okay, so we are still in module 4, and we are still in the big topic, process flow diagram, right? So we just go to another example. This is an online university, and it happens to be our homework 1, question 22. Okay, so for any university, you have to apply, you get admitted, and then you register, right, or enroll in the university. So that's a starting point. So this is the same for this online university. Students have to get enrolled first, enroll in the university. And then after that, they can start taking classes, right? So they have to go through the first stage. So the arrows points at, says that they have to go through, right? And this is our first stage. Stage number 1. They take classes in this stage, and then when they are done with it, they move on to stage number 2. And when they are done with stage number 2, they move on to stage number 3. And then they will do the concentration courses, right? The capstone courses, so that they have the practical skills for their future job. Okay. So stage 1, 2, 3, and 4, and eventually they would graduate. Right. So that's how it looks like. That's a 4-year or 5-year education. But you know what? Life is not that straightforward for everybody. Some students, because of some kind of life-changing event, or they have a better option somewhere, they just quit the university. Okay, so there's some other possible exit point of this process. Some student might quit after the first stage. Yeah, Elita, we assume that we don't have any wait time here. There's no triangle at all, because it is an online university, right? You just go in, move on all the time. You're right. Okay, so we have sometimes student quit after the stage number 1, so we call that as a dropout number 1. Right. And then we have dropout number 2, if someone drop out after stage 2. And then we have dropout number 3. And then finally, right before graduation, right? Some students, because of some very special event, they cannot finish it. Oh, drop number 4. Sometimes students get a good job, they cannot wait, they just go for the job, and then they still have some classes left to finish. Okay, so this picture, right, tells us how the online university process structure, how the student will have to go through, right, that process. So we see the entry point, only one entry point in this case, and we have multiple possible exit points, right? Depending on everybody will have their own experience through the university. And we have 4 stages or 4 activities or 4 steps or anything, right? Yeah, this is homework 1, question 22. I'm helping you with that question right now. If you do this on your own, it might be very difficult, right? Okay, so here's the thing. I give you in the question, I give you the flow time. Flow time number 1, how long it takes through the first stage, how long it takes through the second, the third one, the fourth one. Okay, those are the flow time. On average, how long it takes for the student to go through each of the stages. I gave you all of this in months, but to do the calculation correctly, you need to convert them to the yearly measurement, right? So let me make a very important note out here that you need to convert everything into the yearly number or yearly data. Right. So beside the flow time, you know what? I give you the inventory of stage number 1, the inventory of stage 2, of 3, and of 4. Okay. If you read the question, you're gonna see that some of you might read it already, but with this graph, with this diagram, now I hope that you see more light in it, right? Okay, so the whole university is a big process. And in this case, we break it down into 4 sub-processes, right? Sub-process 1, 2, 3, and 4. And I give you the inventory, I give you the flow time, right? Then we are ready to apply the Little's law. So if you apply the Little's law, you can find the flow rate here. That's a flow rate through stage number 1. And then that's a flow rate through stage 2, flow rate through 3, flow rate of 4, right? So yeah, all the green numbers are the given numbers, and now you can calculate the red numbers. So you find the flow rate 1, 2, 3, and 4. And then after that, I would like to ask you for the dropping out numbers, right? So what would be drop out number 1? What is drop out number 2? Drop out number 3? For drop out number 4, you know what? I gave it to you. But remember, you have to convert everything to the yearly data or numbers or measurement, right?
Professor.
So, yeah. See.
So I think the job 4, since the job 4 has already been passed through the step 4, so why I think that should be completed the whole process. There's no need to job.
We just assume that because of something, then they do not have the how to say the degree at the end. Possibly they miss something. Okay, to simplify it, so to simplify it, we have to assume that the dropout has to happen at the end of the stages. But you are right, T. Normally, when we finish the stage, it means that we would graduate. But in this case, to simplify it, we assume that it happens at the end. Okay. Because of something that they miss, they do not have the degree yet. All right. Yeah, I always try to give the credit. All right, and then so now we already have the. Or does anybody have a question for me? Okay. So we can calculate the job out to 1, 2, 3, and the job 4 is given to you, but you need to convert it to the yearly data, right? Then you can calculate the graduation here. Oh, I have not talked about that yet. Then you will need to find the graduation number, okay? So how to find this? So let me remind you, the flow rate, right, can be calculated using the Little's law. The dropping number 1, you know what, if you look at this picture, the R1 is how many students start the stage number 1. R2 is how many students successfully move on to stage number 2. Then the difference is what? If you take R1 minus R2, we have the job out number 1, right? And then if you take R2 minus R3, then you have job out number 2. Then you do the same to find job out number 3. And the graduation is the difference between how many students started stage number 4 and how many of them drop out after stage 4, right? Then we have the graduation. Does anybody have a question for me at this point? Right. So at this point, you know what? We have the picture, and now we have all the numbers attached to each of the arrows, right? Let me remind you, we are in module 4, we are doing process analysis. So that's why we have to know how the system works, how the process is structured and works, right? So the picture that we have here hopefully helps you to understand the online university. So the arrows here, now we actually know the numbers of the arrows, how much it is, right, per year. Everything has to be per year. Right, so at this point, we know all the numbers. And then the next question is, I would like to ask you, what is the retention rate of stage number 4? What is the retention rate of stage 2, 3, and 4? right? So how to find the retention rate? Retention means that this is a percentage of students that you can keep through the university, right? So if you look at stage number one, for example, if 100 students enter stage number one and 95 of them successfully move on, right? Then the retention rate here is 95 divided by 100, then you have 95%. So that's for one, right? For stage number two, you would take R3 divided by R2 to have the retention rate as stage number two, right? On and on, you can find the 4 individual retention rates. I hope you see that, right? Yeah, if you have anything, Elita, D4, 4 minus G, that's, no, D4 is given. D4 is given, but you need to convert the D4 into the yearly number, okay? So after you find the D4, you take R4 minus D4, then you have the graduation. C, R3 greater than R2, no. R3 has to be smaller than R2. R2 is the number of people who enter stage number two. R3 is part of the R2, move on to stage number three. Some of them drop out, right? So R3 has to be smaller than R2. Yeah, you take the bigger number, subtract the smaller number, right? If you look at it, R2 is how many people enter stage number two. R3 is the number of students who successfully continue, right? Some of them are already drop out here, so naturally R3 has to be smaller than R2 because R2 is R3 plus D2. I hope you see that, right? All right, all of you have very excellent question. That clarifies, that helps clarify a lot of things here, right? For everybody. I really appreciate it. Any other questions so far? You good? All right, and finally, here is the final question in that question. What is the graduation rate, right? So here's the thing. At the beginning of the process, we have 100 students enter the process. I mean, the university, right? At the end, if we have 80 people graduate, then the graduation rate is G divided by R1. And in that case, in that example, we have 80%, okay? So any university, they would look at the graduation rate to see how much student they keep through the 4 or 5 years. The higher, the better, right? It means that they are doing a good job with their education and a lot of things. Sometimes the reputation of the university is also tied up to that graduation rate, right? So, yeah, so this, even though this one is about an online university, but it can be applied to many things in real life. In a manufacturing process, sometimes we have the scrapping, you have to scrap out the goods, right? So eventually, what is the yield at the end? Also, is the graduation rate at the end right here, right? Or if it is an email system or like data bits going to the servers, how many of them are jobs or something like that. So you can apply these then to many things. Okay. So that I hope our discussion here would help you with that question 22 in your homework. So one more time, we have more students here. Let me say it one more time, okay? Homework 1 is due next Monday. All the connect items are due next Monday, including the reading assignments and the 20 online questions are due next Monday, okay? Exclusively on Connect. And for part 2, we do not cover everything yet, so only question 21 and 22 are due next Monday. Question 23, 24, and 25 are due on a later date, and I will make the announcement on that. So does anybody have a question for me at this point? Lita got a question about the retention rate for stage 1. All right, so for stage 1, you just take R2 divided by R1, right? For example, if 100 students enter, and then 95 of them move on, meaning 5 of them drop out, right? So you would take the 95 divided by the 100, R2 divided by R1, then you have the first retention rate. Is that good? Okay, so I hope it's good so far, right? In case if you have any questions, please always ask me. All right, so we are done with this example. And today we move on to the second big topic of module 4, which is about the level 1 analysis. So let me start the notes new. Okay, so next we go to level 1 analysis. Right. So at the end, we're going to have 3 levels of analysis. This is the first level. In this level, we are looking at processes with only one step and only one flow unit type. To make it shorter later on, we just use an acronym of FUT. Right. So this is a very simple process. We only have one stage through, and we only consider one flow unit type. Later on, you're gonna work on one example about it. So the very first concept that we learn here is called the processing time of a resource. The processing time of a resource is how long it takes the resource to process one flow unit through. So let me give you one quick example about it. It's in the slide, so let me read that for you. If you look at the slide on slide 12, the module 4, slide 12. Okay. Cardiac surgery, it takes 4 hours per patient. It means that the doctor will take 4 hours to treat a patient through, right? That's a processing time right there for the doctor. The doctor is a resource in this process, and then it takes the doctor 4 hours to process one patient through or treat one patient through, right? The second example here is in a car factory, it takes the workers 50 seconds to put on the rear view mirror, right? So so that's a processing time to put on the rear view mirror. The next example is underwriting a simple small business loan, 40 minutes per loan. So this is a very simple loan. The amount is not that big, for example, like 10,000 or 20,000 or something like that, right? So the loan officer can just look at the paperwork, and if everything is there, then he or she might make the decision after 40 minutes reviewing the application. Okay, so that's a processing time, right? The loan officer takes 40 minutes to review a loan application. And then the next example, simple transaction call in a bank call center, 5 minutes per transaction, okay? So in this case, right, it takes the operator 5 minutes to answer a call. That's the processing time of the operator, right? And the final example on slide 12, primary care encounter, 15 minutes per patient. So in this case, right, your physician can see you within the 15 minutes, right? You can finish the visit for you in 15 minutes. So that's the processing time of the physician. Right? Primary care means that it is the first point of contact in the healthcare system where you see your physician, the doctor that you first meet, right? And after that, through the physician, you have the referrals to see the specialists. But primary is the first point of contact in your healthcare system. So the processing time is a very simple concept. How long it takes for the resource to process one flow unit through, right? Together with that, we have a closely related concept called the capacity of the resource. Okay, so the capacity of a resource is calculated as the following. It is a flip of the reciprocal of the processing time. Right, the equation looks very simple. Through the next example, you're gonna see how they are related. So I would like to show you the next example. I mean the example of this. So we talk about the first example on slide 15, which is about a color printer. So this is module 4, slide 15. It takes a color printer 10 seconds to print a large poster, okay? What is the capacity of the printer expressed in posters per hour? So if it is a large poster and it takes only 10 seconds, this printer is a state-of-the-art printer. It's very powerful printer, right? So let me summarize the information here. So we have a printing process. And then inside in that process, we have the key resource, which is a printer. So inside FedEx, Kinko, right? There's a business called the printing business. That's the process. And then to do that, they have all of the printers. All right, so the posters will come in. In this case, the flow unit are the posters, right? And at the end, the posters will exit, meaning that they are printed out. And here is the information given by the question. So the processing time of the printer. By the way, if you look at the picture, right, the printer is only the resource, where the process is the whole thing. All right, so the processing time of this resource is given to be 10 seconds per poster. All right, so that's the information that we have. And the question is, what is the capacity of the printer expressed in posters per hour? So we need to find the capacity of the printer. So the way to calculate it is we just use that equation. We flip the processing time, then we would find the capacity. All right, so let's flip it. So we take 1 divided by 10 seconds per poster. Right, let's see why it is true. So when you take 1 divided by that, then the poster will be flipped up to the top right. So we have 1 poster per 10 seconds. And that's true. If we say that it takes 10 seconds to print out 1 poster, then it means that the capacity of the printer is the printer can print out 1 poster for every 10 seconds, right? Per 10 seconds or every 10 seconds. And so in daily life, right, we say the same information in 2 ways all the time. Either you say it as it takes a poster 10 seconds to print out. It takes the printer 10 seconds to print 1 poster. Or you can say that the printer can print out 1 poster every 10 seconds, right? And we keep the same information. So the capacity and the processing time are just the flip sides of each other. They are just a reciprocal of each other in math and also in daily language. So, but then the question doesn't stop here. They ask posters per hour. So we need to convert these to the hours, right? So let me continue a little bit here. So we have 1 poster per 10 seconds, and we need to convert to the hours. So we do it as 1 divided by 3600 of an hour, right? So in this case, the poster will stay on the top, the hour will stay at the bottom. The 3600 will be flipped up to the top, divided by 10. So our answer will be 360 posters per hour. Is that good? Right? So in this case, we know that it takes 10 seconds to print 1 poster. Then in 1 hour, the printer can print 360 posters. It's a very fast process. This printer is a super duper printer. Okay, so so that's the answer. That's how we find the capacity of a resource. We just flip the processing time. The processing time is like the primitive information, and based on that, we can find the capacity of the printer. All right, so that's the first kind of concepts. And now let's move on to the next concept. So we already defined the capacity of the resource, and now let's define the capacity of the process. The capacity of a process is just the maximum number of units that can go through the process per time unit. Right? Like per hour, per day, per week, per month, per year. So this is the number of flow units that can go through the process at most, right? That's why we call it as a capacity. The maximum at most. All right, so at this point, I think that I would like to talk about the next example so that we can make sense of these concepts. So let's talk about the example on slide 15. So another example on slide 15. Earlier, we talked about the first one, and now we have the second on slide 15. So this is about a call center. So what do we have here? Let me read the information for you. A call center has 1 operator who answers incoming call. Right? Only 1 operator answering incoming calls. It takes the operator 6 minutes to answer 1 call. Question 1, what is the capacity of 1 operator expressed in calls per hour? Question 2, what is the capacity of the call center? Question 3, what is the capacity of the call center if 2 additional operators are hired? Right. So yeah, there are a lot of questions here, and they sound like the same. So let me draw a picture, and then we can differentiate among the questions. So we have the process as a call center. Right, that's a whole process. At the heart of that call center is the operator. Okay, the operator will answer the calls. So the flow units are the calls, right? And they tell us it takes the operator 6 minutes to answer one call. So in this case, we know that the processing time of the operator is 6 minutes per call. Probably in real life, we also have this 6 minutes, 5 or 6 minutes, right? The reason why we have to wait for so long is because there's a inventory inside the process, and then we have to wait for other callers to complete their calls before we can talk to the operator. Other than that, the talk time normally like 5 minutes or 6 minutes, right? So, all right, so we already talk about the talk times here, and when we assume that there is no wait time. Okay, so question number 1. What is the capacity of one operator expressed in calls per hour? So in this case, right, we know the processing time of that resource, and now our task is to calculate the capacity of that operator. Right, so I would like everybody in our class to try this and share, and please share your answer in the chat window. So what is the capacity of this operator? How many calls that this operator can handle in 1 hour? So that's the question. Please try and share. Okay, so I got the first answer from C. And about other students, please try and share. From Ing, from or a lot of names already. I could not read it from Michael, from Tristan. You know what? Because the other Zoom is got a frozen, so I cannot see all of the names. Let me try it. Let me try something. Okay, so I see a lot of contribution already. Good. I would like to thank you all. So, okay. Good. I believe that everybody here gets it correct. I really appreciate, and I'm very glad that you already get it. Good. So, all right. So let me work on this with you formally. I believe you know how to do it, but let's work on this formally. The capacity of the operator in this case is a flip side of the processing time, right? So we take 1 divided by 6 minutes per call. Then the call will be flipped up, right? So in a daily language, we might say it as the operator can handle 1 call every 6 minutes. Right? The same information right there. We just say it in the other way. So we do not end here because the question and answers to be per hour, right? So we do that as one call per 6 times a minute is 1 divided by 60 of an hour. So we take the 60 flipped up, the call and the hour will stay where they are, right? So finally, the answer is 10 calls an hour. Of course, in this particular example, we don't have to go through this lengthy process. If it is one call per 6 minutes, then the 10 times of that would be 10 calls per hour, right? So intuitively, we can solve this very quickly. But remember, in the future, we might have to deal with a very complicated situation with the decimal numbers or anything. In that case, right, we have to use this formal process to go through it. Otherwise, it's kind of confusing. I hope you see that, right? All right, so that's the question number 1. And here is question number 2. What is the capacity of the call center? All right, so here's the difference. In the first question, they asked us about the capacity of the resource inside the process. But in the second question, they asked us the capacity of the entire process, right? That's a difference. Conceptually, one is a capacity of the resource, and now it is a capacity of the whole process. So I would like to ask the whole class, what is the capacity of this call center? Please feel free to share in the chat window. And here's my hint for you, okay? This is not a tricky question. I got the answer from Nguyen. How about other students?
So for question 2, what is the time unit?
It's also the same per
Per
hour.
hour?
Yeah. It's easier for us to make sense per hour. That's why they also ask that per hour.
Okay.
Does it matter how many operators?
Oh, right at the beginning, they say that there is only one operator in this call center. It's a very good question, though, both of you. Okay, so now, yeah, I see that. Good. So, yeah, so this, again, my hint for you is this is not a tricky question. It's just a question for you to differentiate between the resource and the process, okay? Maybe it looks too good to be true, right? It's a very easy question, actually. So the capacity of this call center is the following. We take 10 calls an hour. And then because we only have one operator, so the answer here is 10 calls an hour. All right. Okay, so sometimes we just overthink about it. They just ask a straight question. Okay, but then in this question, right, it seems like the two values are equal, the capacity of the operator and the capacity of the call center. The values are equal, and sometimes the equality gotta hide the difference between the two concepts. So that's why they ask us the third question. And here's the third question. What is the capacity of the call center if 2 additional operators are hired? So please feel free to share your thought on the third question. Right, in question 3, I believe I have some answers already. Good. Let me write out the information. So we hire two more operators. And we need to find the capacity. We need to find the capacity of the call center. All right, a lot of you should have the answer already. Okay, all of you get the correct one. Okay, but it takes some time to really understand why it is correct, okay? Okay, so let me explain the answer why you are correct through the following graph. So we have the call center right here. The same building, the same process. But this time around, we have more in it. We have operator number 1, operator number 2, and operator number 3. Okay? And based on our daily experience, whenever we call a center, right? We know that we're gonna talk to an operator, and that's it. So just imagine the calls coming in this way, right? And by a switch box, the calls will be split up kind of equally among the 3 operators here. Normally, they will configure they will program the switch box so that it even out the calls among the 3 operators, right? So that's a daily experience that we have. That's why we draw this picture. So at the end, after you are done with the associate, then you just hang up your phone, right? So that's our common experience. And this graph, this diagram actually shows that, right? So we have a parallel structure. The operators are not connected with each other. You only talk to one person, and that's it. So we have a parallel structure inside the process, and that's why the capacity of the whole center is the capacity of operator 1 plus that of 2 plus that of 3, right? And that's why you got the 30 calls an hour. So let me write here the capacity of the call center in this structure, or given this structure, is going to be 10 calls an hour times 3, and that's how we have 30 calls an hour. But if it is a serially connected process, which means that you talk to the first person, and then your call is transferred to the second, and then transferred to the third, right? Sometimes we experience it. Then the capacity is not 10 calls an hour. In that case, it's only 10. I'm sorry. If it is serially connected, then the capacity is not 30 calls an hour, right? If it is serially connected process, it's only 10, because you have to talk to the first and then the second, the third, and the capacity of each one of them is 10. So the capacity of the whole process is only 10 calls an hour. So I hope that my discussion brings out the alert to everybody that we have to really understand what is going on inside the process to find the correct answer, right? If it is a parallel, this is the answer. If it is a serial structure, it's another answer. So in module 4, we are doing process analysis. It means that we have to understand how the process works. So that's why it is an internal look to see the structure, to see how it works before we properly calculate the metrics, and then we make the right decision, okay? So that's the main idea here. So this part of the example here clearly shows the difference between the capacity of the process and that of a particular resource, right? They can be different. All right, so we are done with that example, and now let's move on to the next concept. So the next concept, we talk about the input rate. Oh, sorry, the demand rate first. The demand rate of a process is the number of units which are demanded, right? That's why we call it as a demand rate, or ordered, or required, per time unit. For example, how many burgers are ordered at McDonald's in 1 hour? How many Pizza Huts are ordered at Pizza Hut, okay, per hour, things like that, okay? So we call that as a demand rate, and the demand rate is very important, right? Without demand, why do we have to produce anything? The demand rate is the source of your income right there, right? Of revenue and profit right there. So for any business, we always have to look at the demand rate. The next concept is also very important, and we call that as an input rate. The input rate of a process, of a business, equals the number of units available or ready to enter that process. Okay? It is another important concept too. Let's take GM as our example. In the past, for example, in a big car factory at GM, they produce 1,000 cars, which means the following. In that one day, per day, right? In that one day, they have 1,000 cars worth of parts going in. So the inputs are 1,000 cars a day, even though at the beginning they are not in the form of finished or completed cars yet, but we know that we have enough parts and materials to build 1,000 cars. So in that case, the input rate is 1,000 cars a day. But you know what, 2 weeks ago, around that time, GM announced that they will need to pause some of the factories because they do not have enough computer chips to put in the cars or trucks, right? So they have to close down some of the, the pause, meaning that the workers will not work at all at some factories because of the chip shortage, right? So in that case, the input rate is not 1,000 cars a day. The input rate, for example, is only 100, and they only use the computer chips on some car models that makes them the most money, right? So the input rate, we normally take it for granted, but sometimes it's not that given. We have to manage it right to have the enough input for our production process, right? Sometimes it is a lack of computer chips, like what we have now. Or in the past, they even have to pause their production because they do not have the car seats to put in the cars. Think about it. There are 4 or 5 seats in the cars, and they don't have the seats to put it in, right? So in that case, as a manager, you have to look at the demand rate, but you also have to look at the input rate if you want to maintain a constant flow or a stable flow of your business. All right, so that's why we have to talk about this demand rate and the input rate. And now we have a very important equation. And here's the equation. The flow rate of a process, of a business, equals to the minimum among the input rate, process capacity, and the demand rate, right? We just talked about all three earlier, and now we bring them together in this equation. So it sounds like a mathematical equation, right? Because we find the minimum among the three, but it's not mathematical. This is how a business should operate. A manager should make that decision, okay? So this is a logical business equation to make it more intuitive. It's just a logical business decision. All right, and hopefully you will see that through the next example. Before we do the example, let me draw a picture to represent it. So we have a process like this. We know our capacity. Like how many cars a day, how many burgers an hour, that's our capacity. But then we have to know the input rate. And this one, normally we take it for granted. We think that we will have it, right? But actually, sometimes we do not have the input. And the next number that we also need to know is demand rate. And our flow rate is the minimum among these three. The input rate, the process capacity, and the demand rate. Right? As a manager, I bet that you would make your decision according to this equation. Why? Let's see this equation, look at this equation through one example. Let's talk about a printing business, okay? We do not have this in the slide, so it's just an example that I give you. All right, so we have a printer with a capacity of 360 pages an hour. Right, in 1 hour, that printer can print out 360 pages. And we would need to look at this printing business through three scenarios. So we have scenario number one. On that particular day, the input rate is 1,000 pages per hour, which means that we have plenty of paper inventory. We have plenty of papers in the back storage. Okay, we have plenty of them. The printer capacity, process capacity is 360 pages an hour. And the demand rate is 400 pages an hour. Okay, so we have a business situation. We have the input, the process capacity, the demand rate. I would like to ask the whole class, how many pages would you print out per hour given this information? Please feel free to share in the chat window. Okay, so I have that from Dylan, from Christopher C. All right, so as a manager, how many pages would you print out? And by the way, we call that as a flow rate, right? How many pages are flowing through the printer or anything like that? All right, I'm very happy that everybody gets it correct. So let me draw a picture to illustrate why we are all correct. All right, so we have the process right here. That's our, let's call that as a printer, right? Even though the printer is only the resource inside the process. We have plenty of inventory, papers inventory. So I purposefully draw the input rate to be quite big, right? Let me draw it. That's our inventory. I'm sorry, the input rate. That's the process capacity of 360. This is 1,000. No, this is why it's somewhere else. And then the demand rate is 400. That's the demand rate. So we have a lot of inventory. We have a lot of demand, but the flow rate, you know what, is only 360, right? So to illustrate it, I just draw the flow to be equal to the process capacity like this. Even though we can sell more, even though we have a lot of inventory, paper inventory, but then we only printing out 360 pages an hour, right? Can we do 400? Even though we can sell 400, but we cannot do 400. So that's why we do not do 400 here. Can we do 300? Yeah, I would like to have a quick answer from you. Can we print out 300 pages an hour?
Yeah.
You just say yes. Oh, okay. See, so yes. But is that desirable?
No, we could print 360.
That's right. Because if we do only 300, we voluntarily cut down our own revenue and profit. No good manager would do that, right? So in this case, logically, given the three numbers, we will max it out. We try to max out by finding the minimum among the three values. And that's why we got the equation earlier. It looks like a mathematical equation, but actually it is a business equation where we always try to max out what we can do to max out the revenue and profit, right? Okay, so let me remind you that in the equation to find the flow rate here, we will find the minimum among 1,000. I follow the order of the three numbers here, right? And then 360, and then 400. And that's how we have 360 pages an hour. And in this case, we have a capacity constraint K. Constraint business situation, right? That's the case. All right, we are short on time, so let me. So I hope that you see the logic behind this equation, right? It's not mathematical. It is because we always try to do the most that we can do. So we will select the minimum among these three numbers to produce. All right. So I would like to give you two more scenarios, and when you go home, please think about it. In the second scenario, the input rate is, to be consistent with myself, let me check out my own data, is 200 pages an hour. Process capacity is the same because we have the same printer, right? And the demand rate is 400, the same as before. But for example, because we do not manage our inventory or the supplying process correctly, so we run low on the papers and we do not know. So on that day, we find out that we have few papers left, right? That's why the input rate is low. So in this case, please find out the flow rate, find out the constraint of this process. And I believe it is easy for everybody now, given what we did earlier, right? Scenario 3, the input rate is 1,000 pages an hour. The same printer as before. But the demand rate is only 100 pages an hour, right? It is a low time for business. So we do not have too much orders. right? So that's why we have it like that. So please also figure out the flow rate and what the constraint of the process, all right? And then please follow the same logic as before. So yeah, I would like to end the class now, and have a great rest of your day. And I will see you back on Wednesday when we do more. Thank you all.
Thank you.
Thank you.
Thank you, Professor.
Thank you. Yes, I cannot catch it up. Thank you.